Hello and welcome back to Hilbert Spaces, the video series where we talk about inner products, operators and related stuff. And in today's part 2, we will look at examples for Hilbert Spaces. However, before we start with that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a supporter, you can download additional material for the videos like quizzes or PDF versions. And these can definitely help you to understand the topics we discuss here. And in this video course, the crucial element you should understand is the definition of a Hilbert space. This one we have already discussed in part 1, so let's quickly recall it here. In a short description, a Hilbert space is just a pair consisting of a vector space X and an inner product. Moreover, as you already know, we discuss real vector spaces and complex vector spaces together. Therefore, we always say that we have an F vector space where F stands for the real numbers or the complex numbers. This is important because the second ingredient here, the inner product, has values in this field, so we map into F. And now, as we have discussed in the last video, such a map here is called an inner product if it has 3 properties, namely it should be positive definite, linear in the second argument, and conjugate symmetric. Okay, and then what we get here is a so-called inner product space, and it gets a Hilbert space if it is complete. In other words, our vector space X also forms a so-called Banach space. And the corresponding norm here is simply defined by using the square root of the inner product. So this is something you should definitely remember for this course. A Hilbert space is just a very special Banach space. So you could just say it's a Banach space where the norm comes from an inner product. And therefore it's not a problem at all to write down some important examples. The first one we really know from linear algebra, namely it's Cn. And usually the inner product we have on it is the standard inner product. But now if you know some linear algebra, you also know some other inner products. And indeed, we also get a Hilbert space with respect to these other inner products. In other words, on Rn and on Cn, we can just fix an inner product and we get a Hilbert space. Indeed, this is something you can remember. For finite dimensional vector spaces, the completeness property here is not a problem at all. It's easy to show that finite dimensional normed vector spaces are always complete. And this means that in this series here, we are definitely more interested in the infinite dimensional case. And one important example there is given as a space of sequences. It's called small l2, where we can also put in n and c. This means that n is the index set of the sequence and c gives the set of possible values of the sequence. And then this L2 describes the set of sequences which are square summable. And a common way to write a sequence would be given as x with index n, where n comes from the natural numbers. And here in the complex case, we want to have the property that xn is for every n an element of C. And now in addition, we also want to be able to sum up the absolute value squared of xn. This means if n goes from 1 to infinity here, we get out a finite number. So we don't go to infinity. So this is the whole definition as a set and as a complex vector space. And now it turns out that we can easily define an inner product as well. So what we have to put in here are 2 sequences y and x. Hence the whole sequence xn from before is simply shortened as the vector x. And indeed, now we can do the same thing as we do for the standard inner product in Cn. Namely, we just sum up the products of the components. So more precisely here, we have yn times xn. And since we work in the complex numbers here, we also need the complex conjugation on the first component. So there you see, this would be exactly the standard inner product in Cn, where n is not an index but a fixed natural number. However, you see the capital N here denotes the number of components in the vector, but here we have infinitely many components. In fact, here we have a sum as before, so it goes from n is equal to 1 to infinity, so it's a whole series. Moreover, one can show that this is a convergence sequence, so what we get out here is always a complex number. This is proven by the so-called Hölder inequality, and you can find it in my functional analysis series. Indeed, there we also discussed a lot about this nice space L2. But now it turns out that one can generalize this example even more. And what we need there is a so-called measure space. It consists of three parts, namely a set omega, a sigma algebra A, and a measure mu. So if you want to see the actual definition of such a measure space, you should watch my measure theory series. Here in this series we will just use the fact that in any measure space we can define the general Lebesgue integral. And then we can also go to the square integrable functions, which we will also denote by L2. However, compared to before, now we have a curved capital L. And usually the information one puts afterwards is just the set omega and the measure mu. And now as before, this is defined as a whole set, which gives us a vector space. And the elements from this vector space are given as functions from omega into C. So we have a function space where we also have two additional restrictions. Namely, the functions should be measurable and square integrable. So if you write down the general Lebesgue integral over omega and you put in the absolute value of f squared, then what comes out is again a finite number, so not infinity. Hence, what you can immediately recognize here is that this is a generalization from our small L2 space from before. Of course, a sequence is simply a map from n into C. And a sum or a series is a Lebesgue integral with respect to the counting measure on n. However, now in the general case, we have a small problem. Namely, we could definitely define the norm of f in the same sense as before. This means take this finite integral we have and take the square root of it. Then what comes out is a finite number, even a non-negative one, but we don't get a full norm necessarily. This is simply because such an integral could give us the value 0 even if we don't put in the 0 vector. You already know that from real analysis you could have a function where the integral is 0. The simplest case for the standard Lebesgue integral would be a function with a jump. Obviously, this is not the 0 function in the space, but it has a norm of 0. And this is simply not allowed to happen for a norm in a vector space. And the solution for that is to simply change the whole vector space here. And the new vector space we get out is denoted by a non-curved capital L. And mathematically, it's simply defined as a quotient vector space. So we take our original curved L2 and we divide by another vector space. And this one we write with a curved n. In fact, this n is not so complicated, it just consists of all the functions that have this problematic property. So we have all functions f from omega into c which are measurable as before, where this new norm is equal to 0. Hence, these are indeed the functions we want to divide out of the vector space. So in other words, what we get out here is a set of equivalence classes where two functions from L2 are equivalent if their difference lies in n. Hence, in the following, one just looks at the equivalence class of a function f. And of course, for this one, we can also define a new norm, simply by taking the original norm of the function f, which represents the whole equivalence class. And then first we can check that this is well defined, and we get a full norm out in this case. Simply because all these problematic functions from before now lie in the same equivalence class as the 0 function. So what we get here is a nice normed space. Moreover, one can also show that we have a Banach space in this case. Therefore, it should not be a surprise that we also get a Hilbert space with a given inner product. Indeed, this is the reason we consider the square integrable functions here, because they lead to an inner product. And now, in order to be precise, we have to formulate the inner product with equivalence classes. And there we represent the first equivalence class with a function g and the second one with a function f. And then, as you might already expect, the inner product is given as an integral. And inside the integral, we just have to multiply the functions g and f. And then we simply integrate with respect to our measure mu. And now the last thing you should not forget, because we deal in the complex numbers, we need a complex conjugation on the first argument. And that's it. This is the definition of the inner product we deal with in the capital L2 space. And of course, you might already know the most important case here, namely the Lebesgue measure on the real number line. Then we just have a standard one-dimensional integral here, and we get the L2 space on R. However, now you have seen the general case and the general construction for a measure space. This is really helpful because this description here already gives us a lot of examples for Hilbert spaces. And please don't forget, being a Hilbert space means that we have a geometry given by an inner product. So for example, the concept of orthogonality even makes sense in such an abstract case. This is what we will do in the next video. We will talk about orthogonal vectors in a general Hilbert space. So I really hope we meet there again and have a nice day. Bye bye.